In this episode, we're going to take something that sounds like pure chaos, randomness, and turn it into a tool for understanding uncertainty in a calm, structured way. Many beginners assume randomness is what happens when you do not know what you are doing, but in data analysis and artificial intelligence, AI, randomness is often a deliberate strategy for learning about a system you cannot fully observe. The trick is to stop thinking of randomness as a fog and start thinking of it as a flashlight you can point in many directions to see what is likely, what is rare, and what is sensitive to small changes. Monte Carlo simulation and bootstrapping are two methods that use repeated random sampling to approximate answers that might be hard to compute exactly. You do not need to be a mathematician to use these ideas well, but you do need to understand what question each method answers and why repeating the process many times makes the result meaningful. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first big idea is that Monte Carlo simulation is not about guessing. It is about sampling from a model of how the world could behave. When you run a Monte Carlo simulation, you define a process that includes uncertainty, then you let it play out many times to see the distribution of outcomes. If the process is realistic enough, the collection of simulated outcomes teaches you about probabilities, ranges, and risks. Beginners sometimes think simulation is only for fancy physics problems, but the same logic applies to everyday data questions, like estimating the chance that a metric crosses a threshold or the likely variability in a performance measure. The output of a simulation is not one answer. It is a shape of possible answers, which is exactly what you need when uncertainty is unavoidable. The exam often tests whether you understand that simulation produces an approximation that improves with more samples, not a single guaranteed truth. A useful way to ground this is to picture the difference between a single roll of a die and thousands of rolls. One roll gives you an outcome, but it tells you almost nothing about the overall behavior of the die. Many rolls reveal patterns, like the long-run frequency of each face, and they also reveal variability, like how much counts can fluctuate in short stretches. Monte Carlo simulation takes that same idea and applies it to more complex situations where you cannot simply reason the probability in your head. For example, if a system has several uncertain inputs that interact, the combined uncertainty can be hard to calculate exactly. Simulation lets you sample input values repeatedly, run the process, and observe the output distribution. This makes it easier to answer questions like what is the likely range, how often do we exceed a limit, and which input matters most. Monte Carlo methods are especially helpful when you care about a function of uncertain values rather than the uncertain values themselves. Many data questions are like this, because you might not care about each individual measurement as much as you care about an aggregate, a ratio, a cost, or a decision threshold. Suppose you want to know the expected cost of errors in a classifier when the costs are different for different types of mistakes. Even if you know the approximate error rates, the actual cost can vary due to randomness in which cases appear. A simulation can sample cases according to those rates, apply the cost rules, and build a distribution of total cost outcomes. Once you see the distribution, you can discuss typical cost, worst-case tails, and how stable the cost is across repeats. For exam purposes, the point is not to compute a cost number perfectly, but to recognize that Monte Carlo provides a practical way to estimate uncertainty in a derived quantity. It is also important to understand what makes a Monte Carlo simulation trustworthy, because the method is only as good as the model you simulate. If your simulated process does not resemble the real situation, then repeating it many times just gives you a very confident wrong answer. This is why defining assumptions is part of the method, not a boring detail you can skip. You must decide what distribution your inputs follow, whether inputs are independent or related, and whether rare events are possible. Beginners often assume independence by default because it makes thinking easier, but real systems often have correlations, like user behaviors that cluster or sensor errors that drift together. A good simulation respects these relationships, at least at a high level, so the results reflect plausible worlds. On the exam, This shows up as questions about choosing when simulation is appropriate and what kinds of assumptions must be checked. Another core concept is the law of large numbers, which is the reason repeated random sampling becomes stable rather than staying noisy forever. The law of large numbers says that as you take more samples, the average of those samples tends to settle toward the true expected value, assuming the samples are generated from the same underlying process. This does not mean every run will be close, and it does not mean randomness disappears, but it does mean that randomness becomes predictable in aggregate. Monte Carlo simulation relies on this stability because you approximate a quantity by averaging results across many simulated runs. Beginners sometimes run a small number of trials and feel confused when results jump around, but that variability is expected when the sample is small. As you increase trials, the estimate becomes more precise and the distribution of outcomes becomes clearer. The exam may test this idea indirectly by asking how changing the number of simulations affects reliability. Now let's shift to bootstrapping, which is related in spirit but answers a different kind of question. Bootstrapping is a resampling method used when you have a dataset and you want to understand the uncertainty of a statistic computed from that dataset. The key detail is that bootstrapping does not require you to assume a specific underlying distribution as strongly as many traditional formulas do. Instead, it treats your observed data as the best available approximation of the population and then samples from it repeatedly with replacement. Each resample is like a new pretend dataset of the same size, built by reusing some observations and leaving out others. You compute your statistic on each resample, like a mean, a median, a model performance score, or a regression coefficient estimate. The spread of those bootstrapped statistics becomes your window into uncertainty. Sampling with replacement is the part that tends to confuse beginners, so it is worth slowing down and making it feel intuitive. When you sample with replacement, you allow the same observation to appear multiple times in a resampled dataset, and you allow some observations to be missing in that resample. That might feel wrong at first because in real life you cannot duplicate a data point, but bootstrapping is not claiming the duplicates are new reality. It is creating many alternate versions of what your sample could have looked like if you were to sample again from the same population. Since you do not have the population, you use your sample as a stand-in. The duplicates and omissions reflect the natural variability of sampling, and that variability is exactly what you want to measure. When you accept that bootstrapping is a controlled thought experiment about resampling, the method becomes less weird and more practical. Bootstrapping is often used to build confidence intervals, which are ranges that estimate where a true value might lie given sampling uncertainty. The idea is that if your dataset is only one sample, your computed statistic could have been different if you had collected a different sample. Bootstrapping simulates that alternate sample reality by resampling your existing data and seeing how your statistic varies. If the bootstrapped statistics cluster tightly, your estimate is stable, and if they spread widely, your estimate is uncertain. This is powerful for beginners because it replaces abstract formulas with a concrete mental process. Repeat, recompute, observe spread. In a data AI context, you might bootstrap a performance metric to see how much it depends on the specific sample of cases you happen to have. On the exam, you might be asked why bootstrapping helps when analytic confidence intervals are hard to derive. It is also important to see how Monte Carlo and bootstrapping differ, because people often mix them up since both involve repeated sampling. Monte Carlo simulation typically starts with an assumed model for inputs and generates synthetic outcomes from that model to approximate a probability or expectation. Bootstrapping starts with observed data and resamples that data to approximate uncertainty about a statistic or model result. In Monte Carlo, the randomness comes from the modeled process you define, while in bootstrapping, the randomness comes from the resampling of your actual dataset. If you want to estimate the probability of a future event under certain assumptions, Monte Carlo is often a better fit. If you want to estimate how uncertain your current estimate is given limited data, bootstrapping is often a better fit. Keeping this distinction clear helps you pick the right method quickly, which is exactly what timed exam questions often ask you to do. Both methods also come with failure modes, and understanding those failure modes is part of using them responsibly. A Monte Carlo simulation can fail if the model assumptions are wrong, if you ignore dependencies that matter, or if you use too few trials and mistake noise for signal. Bootstrapping can fail if your dataset is not representative of the population you care about, because resampling a biased sample just reproduces bias. Bootstrapping can also be misleading when the data has strong structure you break by resampling, like time series data where order matters, because naive resampling assumes observations are exchangeable. Another issue is that both methods can give a false sense of certainty if you focus only on a single summary and ignore the distribution shape, especially the tails. The exam might probe this by asking what assumptions must hold or what caution is appropriate when interpreting results from resampling methods. The safe mindset is that these methods expose uncertainty, but they do not magically fix bad data or bad assumptions. A beginner-friendly reason these tools matter is that they help you reason about variability in model training and evaluation without needing to pretend everything is perfectly stable. In many real datasets, small changes in sampling can change performance metrics, especially when datasets are small or classes are imbalanced. Bootstrapping can show you that a single accuracy number might look impressive, but it might also vary widely across risk samples, meaning you should not trust it as a stable indicator. Monte Carlo simulation can help you understand how sensitive a decision is to uncertain inputs, like how changing a threshold affects expected outcomes when future data is unpredictable. In both cases, the goal is not to worship the output, but to use it to make better decisions about confidence, risk, and robustness. This mindset fits data AI learning objectives because the exam often tests interpretation and judgment, not just calculations. If you can explain what repeated sampling tells you and what it cannot tell you, you are operating at the right level. Another valuable concept is convergence, which is the idea that as you increase the number of repetitions, the estimates stabilize. Convergence does not mean the estimate stops changing completely. It means the changes become smaller and more predictable. In Monte Carlo, you might track an estimated probability or expected value and see it bounce early, then settle into a narrow band as trials accumulate. In bootstrapping, you might see the estimated spread of a statistic become stable as you generate more risk samples. The practical lesson is that too few repetitions can make your results unreliable, but more repetitions cost time and computation, so you want enough repetitions to get a stable picture. For an exam, you do not need to choose exact numbers, but you do need to understand the direction. More repetitions generally produce more stable estimates. You also need to understand that stability does not validate assumptions. It only means your estimate under those assumptions has become precise. Finally, it helps to connect these ideas back to the bigger theme of turning randomness into insight rather than fear. Monte Carlo simulation uses randomness to explore a modeled future, helping you estimate probabilities and expected outcomes when exact calculation is difficult. Bootstrapping uses randomness to explore sampling uncertainty in the data you already have, helping you understand how stable your estimates are and how wide reasonable ranges might be. Both methods shift your thinking away from single-number certainty and toward distribution-based reasoning, which is a core skill in data AI. They also encourage intellectual honesty because they make uncertainty visible instead of hiding it behind a neat average. When you see variability, you can plan for it, communicate it, and make decisions that are resilient rather than fragile. That is what it means to turn randomness into insight. By the end of this lesson, you should be comfortable explaining, in plain language, what Monte Carlo simulation and bootstrapping are doing and why repetition is the engine that makes them useful. You learn that Monte Carlo starts with a model of uncertainty and generates many synthetic outcomes to approximate probabilities, ranges, and expectations. You learn that bootstrapping starts with observed data and risk samples it with replacement to approximate uncertainty in statistics and model results, often supporting confidence interval reasoning. You also learn that both approaches depend on assumptions, and that repeating a flawed process many times does not make it correct, it just makes it consistently wrong. Most importantly, you build a mindset that uncertainty is not a weakness in data work, but a reality that can be measured and managed. When you can look at randomness and extract a reliable story from it, you have taken a major step toward the kind of reasoning the CompTIA Data AI exam expects.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.